In this video, we're going to go through enthalpy of reaction and bond enthalpies. So I have the same reaction written two different ways. In the first reaction, on the right side, if you notice, I have a delta H value. Okay, so since it is positive, we know that this is going to be an endothermic reaction. If you look at the second reaction, I have the energy on the left side, or the reactant side of the reaction, so I know that energy is needed to make that reaction happen. Okay, so we're going to be using the heat as a conversion factor to answer some questions here. So in our first example, it says how much heat is required to react 2.4 moles of nitrogen with excess oxygen to form nitrogen monoxide. Okay, so we have 2.4 moles of nitrogen, and we also know that we have 180 kilojoules of energy that is in our reaction. So the question is asking us how much heat is required to react the 2.4 moles of nitrogen. So while we do have our energy in the reaction, it doesn't really tell us the full picture. So we have 2.4 moles of nitrogen, and in the reaction we have 1 mole of nitrogen and each mole of nitrogen is going to need 180 kilojoules for the reaction. And if we multiply this out on our calculator, we're going to get 430 kilojoules. So again, each nitrogen requires 180. So if we have 2.4 moles of nitrogen, we're going to multiply that 2.4 by the amount of energy required for each to get the total required for the, in this case, 2.4 moles. All right. Next example. If 25 kilojoules of heat was absorbed in the reaction, how many moles of nitrogen monoxide were produced? Okay, so this one's a little bit different because it's giving us the energy instead of the moles. Okay, so we're going to kind of approach it the same way. So we have 25 kilojoules, and we know from our reaction that we need 180 kilojoules. Now, in the reaction, we have 2 moles of nitrogen monoxide. So we're going to kind of put this in the same step here. So when we multiply this out on our calculator, we're going to get 0.28 moles of nitrogen monoxide. Now the reason we used 2 moles instead of 1 mole was because we have obviously 2 moles on the right side of our reaction, but for every 180 kilojoules of energy that is absorbed, it's going to produce 2 moles of nitrogen monoxide, hence the conversion factor here. All right, number 3 says, if you were to react 7.25 moles of dihydrogen sulfide with 9.34 moles of oxygen, how much heat would be released? And then we have our reaction here. Okay, so let's kind of unpack what the question is asking us to do. So it's asking us how much heat would be released, and it's giving us 2 pieces of information. It's telling us we have 7.25 moles of dihydrogen sulfide, and then we have 9.34 moles of oxygen. How much heat would be released? Okay, so since it's giving us 2 different mole values, we're going to kind of do what we do with stoichiometry, and we're going to need to find like our limiting reactant here. Okay, so obviously we're going to be only producing as much as our limiting reactant allows us to do. So we're going to approach this just like we did our first example, and let's do our dihydrogen sulfide first. So 7.25 moles of dihydrogen sulfide, and we know that, let's see, we have 2 moles of that. And for every 2 moles of that, it's going to release 1120 kilojoules. So negative 1120 kilojoules. Okay, so when we plug that into our calculator, we get negative 4060 kilojoules. Okay, so that's for the dihydrogen sulfide. We're going to do the same thing for the oxygen. So we have 9.34 moles of oxygen. Now for oxygen, it's 3 moles. Same thing. It's going to release 1120 kilojoules. And when we put this in our calculator, we get negative 3490 kilojoules. All right, now, just like when we do a limiting reactant problem with Stoich, we're going to look at these, and we're releasing less heat with the oxygen. So since we're releasing less heat with the oxygen, that's going to be the amount of heat that we're going to release. Okay, we can't release more because we're limited by the amount of oxygen that we have. All right. In a chemical reaction, the bonds in the reactants must be broken and remade into the products. Breaking bonds requires energy, which is endothermic. Forming bonds always releases energy, which is exothermic. Now, you can estimate the potential energy change for a reaction by adding up the bond energies for breaking all bonds in the reactants and then adding up the bond energies for making all the bonds in the products. And then basically what I just said is summed up in this little equation down at the bottom. So delta H equals the sum of all of the broken delta H values minus the sum of the delta H values for all of the formed bonds. So you're going to need a table like this. So on this table, it gives you all of the bond enthalpies. So you're going to need to basically draw out some Lewis structures and figure out what bonds are being broken. The energies are going to be on here, and then you just kind of add them up and do that subtraction to figure out what the question's asking for. So here's an example. It says how much heat is released through the complete combustion of propane, which, if you didn't know, is C3H8. Okay, so like I said, you're going to need to draw out some Lewis structures here to figure out what's going on. Okay, so our C3H8, which is propane, is a pretty big molecule. So let me just kind of sketch this out here, draw a Lewis structure. Okay, so there's our C3H8, and then O2, we have 5 of these, so O2 looks like this. 5 O2s, I should say. O2 is a double bond. Now I'm not drawing like a complete Lewis structure, I'm just kind of sketching this. I know that O2 is a double bond. So there are my 5 O2s, and then this is going to produce 3 CO2s. Okay, so CO2 is, we've got carbon in the middle, and then we have double bond oxygen here and here. Okay, and again, I'm not including all of the dots on these, I'm just really focused on the bonds. And then we have 4 H2Os. Okay, so H2O looks like this. We have 4 of those. Okay, now we want to figure out what bonds are being broken, what bonds are being formed. Okay, so on our propane, we have a CH bond. There are 1, 2, 3, 4, 5, 6, 7, and then 8 of those. Okay. We also have a couple carbon-carbon bonds. So we have 1, 2 of those. And then for our oxygen, we have just a double bond oxygen right here. So we have 5 of those. 2, 3, 4, 5. So these are bonds broken. So what you would do is you would go up to the table and you would look up all of these bonds. So for example, our carbon-hydrogen bond is up here. And our carbon-carbon bond is right below it. That's convenient. And then we have a double bond oxygen. So our double bond oxygen is, where is that on my table? O2, right here. Okay, so I would plug in those values. So we have 8, and CH was 413 kilojoules. Carbon-carbon was 348. And then our O2 was 495. Okay, so I would add all those up, multiply and then add those up, and I get 6,475 kilojoules. Okay, and then our bonds formed. We're going to do the exact same thing. Okay, so for our bonds formed, we have a carbon-oxygen double bond. We have 1, 2, 3, 4, 5, 6 of those. For our waters, we have a oxygen-hydrogen bond. We have 1, 2, 3, 4, 5, 6, 7, 8 of those. And I'm going to go look those values up on my table. So I have a carbon-oxygen double bond, and then I have an oxygen-hydrogen bond. Oxygen-hydrogen OH is right here. Okay, so I'm going to go plug those values in. So our carbon-oxygen double bond was 799, and our oxygen-hydrogen was 463. So we're going to add those up, and we get 8,498 kilojoules. Okay, so now if we subtract bonds broken minus bonds formed, we're going to get negative 2,023 kilojoules. And that would be how much heat is released. Okay, so a tip when you're working these types of problems, when it asks you about this, draw out the Lewis structures. You don't have to draw out the whole thing. You don't have to include the dots, but you want to make sure that you have all the bonds correct for these, and then kind of just work it like I did. Go through and circle all the bonds. Make sure you're not leaving anything out. Look up those values on the table. Add up all the broken, add up all the formed, subtract, and there's your answer. So much fun.